Hello everyone, I am Professor Anish Vora and I welcome you all in this video lecture. Currently, you know that we are running a series of video lecture on design of synchronous machine. In this video lecture, we will study about the design of salient pole type of rotor. In case of synchronous alternator, we know that we use two different types of rotor construction. One is a salient pole type of rotor construction and one is smooth cylindrical type of rotor construction. In case of turbo alternator, we use a smooth cylindrical type of rotor construction, and in case of a hydro alternator, we use a salient pole type of rotor construction. We have studied in previous lectures construction of salient pole type of rotor, but let us revise, and then it will be easier for us that what we should know what exactly we are going to design. So this is field winding. Field winding is wound across the radial length of the projected part of the salient pole. Then this is pole body, main part of the pole, that is pole body. Then we have a pole face, or rather we call it a pole shoe. Then the structure is riveted. We have shaft. All the assembly is across the shaft. Then we have a steel spider to accommodate the projected pole. Then we have damper bars which is accommodated in the pole shoes. So this is our construction, basic or typical construction of the salient pole type of rotor. In this video lecture, we are going to design dimension of the pole as well as dimension of the field winding. So let us see how we can do a complete design of salient pole type of rotor. So sectional area, we should calculate sectional area of the pole, then type of pole, whether it is a round type or whether it is a rectangular type, then height of the pole, field winding design, and at last damper winding design. Both the design, field winding as well as damper winding design, will be doing in our next video lecture. In this video lecture, we'll be designing cross-sectional area of the rotor pole, type of pole, and ultimately will decide the height of the pole. So basically we are going to design dimension of the pole in this video lecture. Let us start with the sectional area of the pole, and we start with the leakage coefficient. In case of leakage coefficient, C and L suffix is for the leakage and C is coefficient. So CL, that is a ratio of the total flux in the pole body and divided by useful flux, and the ratio is known as the leakage coefficient. So by using this ratio of leakage coefficient, that is phi p, that is total flux in the pole body, and divided by phi, that is useful flux. So using this equation, we are easily able to calculate total flux in the pole body, that is phi p, and that is equal to product of leakage coefficient multiplied by useful flux. Useful flux we might have calculated at the initial stage when we calculate or we decide our specific magnetic loading. So CL, that is leakage coefficient, and appropriate value of the leakage coefficient we need to define, and normally we take around 15 to 20% of the total flux. So that is 1.15 to 1.2 can be taken. So we have two different types of rotor pole body. One is a rectangular shape. So that is the breadth of the pole, and this is a length of the pole. In case of axial length, it should be very clear to everybody that axial length that must be equal to the length of the stator core. We take slightly less, that is 1 to 1.5 centimeter less of the pole, because there is a free movement of the pole inside the stator. So axial length should be very much clear. And another construction, that is a round shape. In case of round shape, diameter, that is again a BP. So either it is a breadth or the diameter of the pole. Now cross-sectional area of the pole. If we know the flux density, then cross-sectional area can easily be calculated. We know the equation that for flux density we normally take a equation flux divided by area. So using same equation we can find the cross-section area of the pole body. So AP, that is cross-section area of the pole, area A and suffix P for pole, and that is equal to 5P, that is the total flux in the pole body, and divided by capital B, that is used for flux density, and P is for pole. So cross-sectional area of the pole body, that is 5P divided by BP. So using this equation, if we take appropriate value of the flux density in the pole body, then we can easily able to calculate cross-sectional area of the pole body. So that flux density can be easily 0.5 to 1.7 Weber per meter square. And once we have cross-sectional area available, we can use equation for the area, that is 0.98 multiplied by LP and multiplied by BP. 0.98 we consider for stacking factor, and LP and BP. We know the axial length of the pole body is known, as I said earlier, that it can be considered as normally equal to the length of the stator core, and from this equation easily the breadth of the pole body, or width of the pole body rather, can be calculated. If it is a round type of pole, then diameter of the pole can easily be calculated if we know the cross-sectional area of the pole body. So LP, that is length of the pole, and BP, that is breadth of the pole or width of the pole in case of rectangular pole, and it is diameter in case of a round pole. So one cross-sectional area is available. Now to find the another dimension of the pole, and that is basically height or radial length of the pole, we should know that how to calculate height, overall height of the pole, and it is dependent on the ampere turns to be produced. To produce the flux and flux density, required flux density, we require the magnetomotive force to be generated through ampere turns of all salient pole type of pole and field winding wound across it. So the dimension of the field winding ultimately decide the height, overall height or the radial height of the pole. So let us see the basic construction, how our radial length of the pole is divided or distributed in several parts. So this is one of the salient pole we have taken. Field winding is wound across the length of the pole body. So this is field winding. So this is height of the field winding. So main part is the height of the field winding. And then we have BG, that is a saliency in the salient pole type of rotor. And in between we have space left for fixing the field winding and for the insulation. So we use flanges or we use insulation. So certain space we have left in between. And this is the height of the pole body. So this is height of the pole body, and height of the pole body, that is because of height of the field winding, and we have certain amount of space left for keeping insulation and fixing the field winding. At the center of the pole, we take height of the pole shoes. Some of the height we have wasted because of curvature of the stator yoke, and this is overall or radial length or overall height of the pole, and that is exactly equal to the addition of height of the pole body and height of the pole shoes. So HP plus HL, that is total height of the pole body. This should be known to everybody, and then we accordingly will be going to design each and every part of the height to decide the final height of the pole shoes and pole body. So now we start with the pole height. First we should know that no load field MMF, how to calculate field MMF. As I said earlier, that height of the pole body is decided by the height of the field winding. The required field winding to produce the appropriate value of the ampere turns or a magnetomotive force. The main part to decide the height of the pole body, that is our field winding, height of the field winding or space required for the field winding. So if we consider no load field magnetomotive force, how to calculate, and normally it is considered as a product of ampere turn required for the armature multiplied by short circuit ratio SCR, or normally no load field magnetomotive force can be considered as a 1.72 2 times of the ampere turns required for the armature. And ampere turns required for the armature, it is known or we have calculated earlier, and that is 2.7 product of I phase and T phase. So current per phase and number of turns per phase multiplied by kW, that is stator winding factor, and per pole, so divided by P. And if we know the ampere turns for armature, ultimately no load field magnetomotive force or no load field ampere turns can be calculated as SCR multiplied by ampere turns for the armature. So with this equation, no load field MMF can easily be calculated. So from the no load field magnetomotive force, we require to calculate or we require to estimate full load field magnetomotive force, and let us see how we can decide full load field magnetomotive force. So we draw one phasor diagram as per the scale, and let us start with the no load field magnetomotive force, that is ATFO. So on the x-axis we draw the phasor as per the scale, and we take OA, that is exactly equal to the no load field magnetomotive force, that is ATFO. Now we draw one phasor from the A with an angle with the x-axis, and that phasor is AB. So angle, that is 90 minus 5, and here 5 is a power factor angle. So AB, the length of the phasor AB, that is exactly equal to the ampere turn for the armature. And then we decide one point on the AB, and that point is known as the C. So to decide the C, we take a ratio AC divided by AB. So if we take a ratio of AC to AB, and that is known as a KR or coefficient of cross reaction. So this ratio is basically dependent on the ratio of the pole pitch to pole arc. So if we decide point C, then we draw another phasor from the O and crossing the point C. So we draw another phasor starting from the point O and crossing the point C. Here we draw phasor OD, and from the D we draw a perpendicular phasor from the D to B. This would be at the 90 degree to the OD. Now this length of the OD can be considered as a full load field magnetomotive force, and that is ATFL. So to calculate full load field magnetomotive force is very important, and based on the full load field magnetomotive force, the further designing work of the height of the field winding can be considered. So now dimension of the field winding. Total copper area of the field winding. So total area of the field winding, area, that is a field magnetomotive force for the full load, and that is calculated or estimated rather from the phasor diagram and divided by field current density. So if we choose appropriate value of the field current density, and we know full load field ampere turns, so total copper area of the field winding can be easily calculated with this ratio. So ATFL, that is full load field ampere turns, and divided by delta F. Delta F is current density of the field winding, and normally field current density can be taken as 3 to 4 ampere per millimeter square. So total copper area is calculated with this equation, and then total space required for the field winding. We have calculated total area required for the field winding, and now total space required for the field winding. So copper area divided by space factor. Here copper space factor normally based on the type of conductor we use. For example, we use a small round type of conductor, then space factor is less, and that is equal to 0.4. These typical values as per the standard table can be taken while calculating the total space required for the field winding. If we use a large round wire, then space factor can be considered as a 0.65. And suppose if we use a rectangular conductor, then up to 0.75 space factor can be used. But normally it is a normal practice to take a space factor between 0.4 to 0.6. So copper space required, total space required for the field winding to be accommodated, from this ratio it can be calculated. And once total space required for the field winding is known, height of the field winding can be easily calculated. So height of the field winding, that is total area of the field winding divided by depth of the field winding. So again, to decide the depth of the field winding, it is purely dependent on the pole pitch. So pole pitch in millimeter and depth of the field winding. So it is very standard to use, suppose the pole pitch is 100, then we use the depth of the field winding 25. With 200 pole pitch, 200 millimeter, we use 35 millimeter depth of the field winding, and for 400 millimeter pole pitch, we use 45 millimeter depth for field winding. So this way we can decide the depth of the field winding And if depth of the field winding is known, we can easily able to calculate the height of the field winding. Once height is available, height of the field winding is available, height of the pole body can be easily calculated, and then overall height of the radial length of the pole can be designed. So alternatively, we have another equation to calculate the height of the field winding. So alternatively, using another equation, we can also able to calculate height of the field winding, and we use this equation ATFL divided by ATFL, that is a full load field MMF, divided by 10 raised to 4, and under root product of SF, DF and QF, where SF, that is copper space factor, we discussed that it can be taken as 0.4 to 0.6. DF, that is depth of the winding. Depth of the winding can be chosen based on the pole pitch. In a last table we have seen that how depth of the winding can be chosen. And QF, that is a loss per unit surface in watt per meter square. Normally in between 700 to 750 watt per meter square loss per unit surface can be considered. So from this equation, height of the field winding alternatively we can able to calculate, and once, as I said, height of the field winding is available, then a radial length of the pole, that is a addition of HF, that is height of the field winding, plus HL, that is height of the pole shoes, plus 0.02 meter, that is a space left for the insulation in between, and we require some fixtures of flange to fix the field winding. So HL, that is height of the pole shoes, HP, that is height of the pole body, which is equal to the HF, that is height of the field winding, plus 0.02, as I said, that the space left for the insulation and fixtures. So the ratio of radial length of pole to pole pitch, this is again one ratio we decide. To decide the radial length of the pole, we take this ratio, that is the radial length of pole to the pole pitch, that is taken as 0.3 to 1.5. So based on this ratio, we can calculate radial length of the pole, and the reverse process is also true. If we know the maximum or permissible radial length of the pole, then accordingly we can decide the height of the pole shoes and the height of the pole body. But ultimately again, height of the pole body is dependent on the height of the field winding. So this way we can do the overall designing work to find the dimension of the pole in case of a salient type of pole. In next lectures, we'll be designing our field winding as well as a damper winding. So thank you for watching my video. Keep watching. Thank you very much.